I'm very pleased to be here. But why are you all here? Why are we in this talk about greenness? Well, partly it's because it's a keynote. You don't have any choice unless you want to be out there with the leftovers of the lunch. But why is this talk in this conference? Why am I here? Well, it turns out that our industry has quite a large climate impact. We tend to think of aviation as sort of the poster child for being really irresponsible with the planet. And I carefully took the train here rather than flying so that I could be virtuous. But actually, when you look at it, the digital world creates more carbon emissions than flying, which is bad. Now, when I say the digital world, that includes things like laptops, devices, PlayStations. Maybe that's not actually directly related to us. But if you look just at data centers use as much electricity as a medium country. So the world's data centers use about the same amount of energy as the UK. And if you look at the network traffic in and out of the data center, which of course you have to consider, that's part of what the computer's doing, then that almost doubles the electricity consumption. Because of course we tend to think of the network as kind of magic that goes through the air and gets the data to our computer. But a network is made of switches, and switches are computers. So every time a packet goes across the network, it's going through multiple computers and using energy every time. And the world's data centers, where does the stuff in them come from? It comes from us. Our job is basically to write the stuff that goes into data centers. So that means it's us who are responsible for this electricity consumption. It's us who are responsible for this carbon usage. And I think sometimes, again, it's so tempting to think that it's other people. So, it's not me, it's those people who are writing those really hungry AI models. They're the ones who are using all the electricity. Or, it's those people who are doing the cryptocurrency mining. They're the ones who are using all the electricity. But actually, it's really not. It's all of us. It's the applications that we're writing that have this carbon impact. So that's kind of bad. And at this point, it's kind of tempting to go, climate apocalypse, and it's all my fault. I don't think that's the right response. I think instead, what's much more helpful is to think about solutions. Instead of sort of plunging ourselves into despair, be a solutionist, because there are actually things that can be done. So then the question is, of course, but how? Well, we're starting to now get some pretty good sort of digestible practices for what we should be doing. And my favorite come from the Green Software Foundation, and they have a bunch of principles. And you can divide them into 3 categories. So the first is carbon awareness, and that's really about where your workload runs and when your workload runs. The next is hardware efficiency, which is really about the elasticity of your workload in your infrastructure and the utilization. And then the last one is electricity efficiency, which is really, it's about the algorithms and it's about the stack. I'm going to talk about that one first, because of course, if there's one thing that we as developers love, it's arguing about algorithms and arguing about stacks. And efficiency really is about trying to do as much as possible with the smallest amount of energy. And probably a good place to start thinking about how can we be as efficient as possible is to think about programming languages. And there's 2 reasons for this. One is that the programming language, it's a really big part of the stack. That's going to have a big impact on the energy usage of your program. But the second reason to start here is that we all love a programming languages war. And we all know, as Java developers, that some of those other languages are pretty terrible, and the people using them are pretty stupid. And now, not only are they stupid, they're climate vandals who are destroying the world for our grandchildren because of their bad choice of programming language. And we have evidence. Because there's a paper, this circulated across the internet a few years ago. They were running micro-benchmarks, so do take it with a pinch of salt. But they found some really interesting results. They ran the same suite of micro-benchmarks across about 27 languages. And this is the sort of the summary of the results, the highlights. The first thing to notice, Python. We always knew those Python people were terrible, and now we have the evidence. The next one is a little bit more surprising, because we always knew that JavaScript people were terrible too. JavaScript is actually not as inefficient as you might think. JavaScript has some really interesting performance characteristics about how it does non-blocking I/O and that kind of thing, which means it's not as efficient as Java, but it's pretty okay. Another interesting thing to note here is that Java is more efficient than Go. So next time people say, oh, well, you Java people, we always knew you were terrible, you should be using Go, we can say, even though Java is a compiled language and Go is native, actually, we're more efficient. The other things, of course, is that those C people, they are actually right. C is very efficient. And those smug Rust people, Rust is pretty efficient too. But it's about a factor of 2, so there's not that much in it. So here's the sort of the whole table. And again, you can see that Java is up there at number 5, which is a pretty healthy place to be. Because when you consider how nice Java is to use, number 5 is OK. But then we can go further. So if we are going to use Java, what's the most carbon-efficient way of programming our Java? Things like the GC tuning parameters can make a big difference. Those can make, again, a factor of 2 difference to our application. But there's something else that can make a difference, which is, of course, the next level up from the programming language is our framework. Now, my day job is that I work for Red Hat. I work on Quarkus. I've been with Quarkus for about a year. And when I joined the Quarkus team, one of the first things that everybody told me is that Quarkus has really amazing performance. So it's got these ridiculously small footprints. It's got ridiculously small startup time. And so then the question is, OK, so if we've made this runtime that's really small and light and fast, does that mean that it's got a reduced carbon footprint? Intuitively, it seems like it must. But of course, the first rule of performance is you can't just go on your intuition. You have to measure, not just guess. Now, turns out measuring carbon is kind of hard. The first thing that you need to do is you need to measure the power usage. The ideal way of doing this is that you just plug something into the wall to see how much power the computer's sucking out. That's quite complete, but unfortunately, you need physical access to the wall, and then you need specialized equipment, and then it's sort of not digital. So a much more convenient way of doing it is that Intel processors have something called RAPL. So RAPL, you can just program it. It's programmatically accessible, and then you can get your carbon measurements. It's not your electricity measurements. It's not quite as complete as at the wall, but it's so much easier that it's totally worth it. But no matter which way you're doing it, of course, you're not counting the network usage and the data. But we'll ignore that. Because we have a bigger problem, which is that most of us aren't running our workloads on a computer under our desk that we can just plug something into the wall. We're running them in the cloud. And the whole beauty of the cloud is that the cloud is a black box. We cannot actually physically access those machines. We can't even get to the infrastructure of the machines. The good news is that we can get a lot of the way there. If we know the load, then there's now some open source data sets that allow you to go from the load. If you know what your load is, and you know what your instance is, and you know where you're running, you can go from there to an estimate of the power usage. Once you've got the power usage, you can convert your power usage to a carbon, because how much carbon the electricity uses depends whether it's going to be wind or solar or coal or whatever. And you know how the power was generated if you know where the workload is running. Because every region in the world has an energy mix. So, for example, in the Nordics, the energy tends to be largely renewable. These aren't great because the methodology that every cloud provider uses isn't open and it's not consistent, so you can't compare across cloud providers. But within a cloud provider, if you're optimizing, you can get a lot of the way there. And the last thing that you need to think about is the embedded carbon. So this is the cost of actually manufacturing the computer that you're running on, because manufacturing has big carbon costs. So that's a lot like hard work, is the downside. I saw some of you as I was talking kind of going, oh God, this sounds really intense. When to the next talk? So the good news is that there are simpler models. Now, when I talk about these simpler models, if there's anybody who knows climate science in the audience, they start to look really, really anxious, and they start to go up, 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 because these simpler models are wrong. But they're useful. And for things like saving the world, I think it's much better to be approximately saving the world than not at all saving the world. So the first simpler model is my first trick, which I call the Vroom model. That's obviously a made-up name. And if we go back to that table of what programming languages were most efficient, you can see that there's actually two columns. The first column is energy, and the second column is time. And you can see that they're basically actually the same. So like C is top, Rust is second, C++ is second, Ada is fourth, Java is fifth. So there's a really strong correlation between how fast the benchmark runs and how much energy it uses. So basically, energy consumption, if you keep everything else the same, is proportional to execution time. That's a really useful heuristic for us. And it means basically we want to write our programs to go as fast as possible to save the world. The second trick is the economic model. This one isn't a made-up name, but it's short for the economic input-output lifecycle assessment, which is why we call it the economic model. And what this model says is that if you reduce your cloud spend or your hardware spend or your electricity spend, and if you keep everything else the same, you're probably reducing your carbon footprint. So, how does that relate to Quarkus? How did that help us understand Quarkus? Well, before I joined the team, a colleague of mine did some experiments where he took a real workload and he ran it on a real cloud for 20 days to actually, not have a micro benchmark, but to have sort of more of a real-world evaluation of could Quarkus save you money? And he found that it definitely could. So here we've got Quarkus native, Quarkus on JVM, compared to a framework from a different vendor. And you can see that we were able to run on a much smaller instance at the same workload. So that already was saving money, but we could use that data set that I described that allows you to go from your load in your instance to your carbon and get carbon estimates for Quarkus. And so you can see there, Quarkus is about half the carbon. And so what's that's kind of showing you, again, this is useful, like even if you're not using Quarkus at all and will never use Quarkus, this is sort of a good illustration of the economic model, because you can see that they're not exactly the same, but they're going in the same direction. They're roughly proportional. But we wanted to do some better measurements that weren't just relying on the economic model. And so we took some on-premise hardware so that we could actually use the Intel RAPL. And we ran some experiments. And we looked at the carbon consumption as a function of load. So the first thing to notice is that, as you would expect, the more load you drive into the system, the more carbon is used. And so higher is worse. So the worst carbon offender was the legacy framework running as a native application, then the legacy framework running on JVM, then Quarkus as a native application, and Quarkus on JVM. And when we got those results, we were a bit surprised, because we were like, wait a minute, native has like a tiny memory footprint and it starts in like faster than a light bulb. Why is it using more carbon? And the reason is because if you run Quarkus on native, or in general anything else as a native application, you get a smaller footprint, but the throughput will be lower. And so this is actually the Vroom model in action. The fact that native has a lower throughput means that it has a higher carbon footprint, even though it seems crazy efficient. And again, this is going to depend on the exact workload and how constrained your environment is and that kind of thing. And we haven't redone the experiments, but GraalVM 23 just came out, and they have some really impressive throughput numbers. So that may shift this and maybe even flip the two. But overall, definitely my third trick, and I work for Quarkus, so they're this is very convenient for me. But I would recommend Quarkus as a climate solution, because just without changing anything else, your workloads run faster and they're cheaper and they're saving about half the carbon. And my colleague has a really nice talk, because we have some Spring compatibility libraries in Quarkus. And so what he does is he takes an application and he just changes the pom.xml so that it's using the Quarkus Spring compatibility libraries. And he doesn't change anything else. And just changing those dependencies, again, more or less doubles the speed and halves the carbon. It's really cool. So what about hardware? So I mentioned elasticity and utilization. Utilization probably should come first, because utilization is how much of the capacity you're using, and elasticity is how easy it is to scale up and down. So if you think of sort of a server, the ideal scenario is that your application is using most of the CPU, memory, whatever, but not all of it. So that's the sort of the good case. The very, very bad case is when you are overutilized, so you can't actually do what you need to do. This is the case that gets people fired. And so in order to avoid that, what we often tend to do is this instead, because nobody wants to be the person who caused an outage by under-provisioning. So instead, we over-provision, and we say, that application is definitely going to stay up. I'm destroying the world, but that application is going to stay up, and I'm not going to get fired. So what do we do in order to try and avoid that case and stay at a consistently good utilization? That's where elasticity comes in. So with elasticity, if our workload scales up, our capacity scales up. And again, the other really important part is that if our workload scales down, our capacity has to scale down as well. And quite often, especially with the cloud, we've got the scaling up part really sorted out, but nobody wants to write the auto-scaling algorithm that causes the outage. So auto-scaling algorithms tend to be conservative about when they scale down. And of course, often we don't even have an auto-scaling algorithm or anything like that, because our industry has absolutely horrible, horrible utilization. So in 2017, they did a survey of servers, and they looked at 16,000, and they found a quarter of them were doing no useful work. And by no useful work, I don't mean that they were serving cat pictures. What I mean is that this thing hadn't had any traffic in or out or had done anything for 6 months. Like, that's a really high bar. And a quarter of them were still completely like that. And then you say, well, how did this happen? And the answer is, perhaps someone forgot to turn them off, which I have been completely guilty of personally. But then there's sort of a second layer to that story, which is that they found a further 29% of the servers were active less than 5% of the time. So that's still really bad. You have all these servers that have been paid for, that have the embodied carbon, that aren't doing anything. And even in the cloud, this still absolutely happens. So we tend to think, I mentioned, we think of the cloud as really elastic. But they tried to work out how much money was being wasted by cloud instances that we don't turn off when we don't need them. $26.6 billion in 2021 was wasted by always-on cloud instances. That's so terrible. That's so much money. But of course, it's not, I mean, the money matters, but it's not just money. And it's not even just the electricity used by those things, because manufacturing a computer uses a lot of water. Running a data center uses a lot of water. And once you've finished with the computer and want to get the next computer, e-waste is a big problem. And so it turns out like the solution for this is really easy, because sometimes even something as simple as just scripting can turn your instances off overnight when you don't need them. And we see really, really good results. So I saw a talk and they saved 30% on their cloud bill just by turning them off out of working hours. And probably a lot of you know Tom Cools. And he told me a story that his wife works for a school in their IT, and she wrote a script to turn the school servers off overnight. And she saved her school 12,000 euros, which is a huge amount of money just for like a simple script. So why don't we all do this? No one wants to be the person who turned the server off when it was needed. No one wants to be the person who turned the server off and then discovered it wouldn't come back up. Because, of course, computers tend to be different when they come back up. But I don't think it doesn't have to be this way. Like, if you think about light switches, nobody ever leaves a room and says, oh, well, I'm coming back to this room tomorrow, so maybe I'll just leave the light on in case it doesn't come back up. We trust that the light bulb's going to come back up. It's going to work. We should be able to architect our computers for that same experience. So it really, it should be that you could turn it off and on again, and it comes back up fast, that the thing actually works and hasn't lost some state that it needed. So that's called idempotency and resiliency as well. And so I think this is something that we should be thinking more about. And so I call this light switch ops. So far, no one else is using the term light switch ops, but I'm hoping if I keep saying it enough and enough and enough, someone will. And apparently, there's an O'Reilly book about sustainability that's coming out in the summer, and I've been told they mention light switch ops. So I haven't actually seen it, but it could be this crazy person says light switch ops, but we think this is a terrible idea. But hopefully not. So, through a combination of architecture and simple, stupid scripts, make things so that they can be turned off and on often. But, of course, like anything else, you have to be able to measure. You can't optimize things if you can't measure them. So I think there's some other management tools that we should be looking at. How many of you have heard of FinOps? Only about 2 or 3 hands. A few more drifting over there. So FinOps is, another one of the sort of the XOps. And it's really about bringing that real-time information flow and automation to a company's financial information. So that's cool. But I tend to think of it, because if you get that real-time information, get that information where it's needed, that's basically figuring out who in your company forgot to turn off their cloud so that you can respond to it more quickly. So I'm hoping that FinOps is going to become more of a thing. Another tool sort of in the same area is Backstage.io. It came from Spotify. It's now been adopted by the CNCF. And there's Backstage is a portal, but there's a couple of quite cool plugins that you can get for Backstage. One is the Cost Insights plugin. So that's really, again, a sort of a FinOps plugin so that you can see the financial impact of your architecture. Because if you can see it, you can optimize it. And then the next one is the Cloud Carbon Footprint plugin, which allows you to see a bit more about the carbon footprint of your architectural decisions. And that matters because where and when you run your workloads matters a lot. And this is my final trick, which is to think about the electricity source. I mentioned earlier that you can get an energy mix for a region. where you run your workloads has an enormous impact because how each country generates electricity, what infrastructure it has available, is really different. And this information is quite accessible to us now. So if you go to electricitymaps.com, they sell the data as an API, but they also have just a nice little map that you can browse, and it's quite fun just to browse. And some of the things are really surprising. So for example, South Africa has incredibly dirty energy. Quebec has incredibly clean energy. I wouldn't have necessarily expected either of those. And in particular, on the data center location, one place, you notice on the previous map, that east coast of the US was pretty brown. And there's a lot of data centers on the east coast of the US, in particular in Virginia. So there's a great big transatlantic data pipe that comes up in Virginia. And so Virginia was a really natural place to build most of the world's data centers. And Virginia had an extra advantage when it came to building data centers, which it had enormous natural resources that allowed electricity to be generated, because Virginia has lots and lots of coal. So that seemed like a really good idea a while ago. Now it seems like a really terrible idea, but of course it's kind of hard to change these things. But if you have a choice, do not run your workloads in US East 1, because it's often at the top of the list, it's the default choice. It's running on coal-powered electricity. And more generally, when you're choosing a workload, I sometimes go eeny, meeny, miny, mo, data residency requirement, eeny, meeny, miny, mo, but actually look at the sustainability information before choosing a region. And if your cloud provider doesn't give you that information and make it easy to find that information, then maybe look at a different cloud provider. Another thing to think about is the time of day, because most renewables are what's called intermittent. So obviously, the sun only shines in the day. You cannot do solar power at night, no matter how you try. Wind tends to be a bit arbitrary when it happens. And if the grid can't meet the demand with renewables, they'll fire up the coal plants. So we really want to make sure that we're not pushing the grid over capacity by choosing when we run the workloads. So I've talked about a bunch of things, and I think one thing to take away from all of this is that it's not all bad. There's a project called the Drawdown Project, and they have this idea of no-regret solutions. And what they mean by this is things where actually you're better off choosing the green solution than you would have been if you'd stayed doing what you did. And I'm not sure that no-regret solutions is the best name, so I keep trying to come up with a different name. So sometimes in climate circles, this is called co-benefits, but that doesn't sound really clear, and it maybe sounds a bit like friends with benefits, and it's just confusing. So I sometimes talk about the double win, but again, I have to spend so much time explaining it, I'm not sure it's actually helpful. Sometimes I talk about win-win, but again, that sort of needs a lot of explanation. For Americans, saying it's a twofer, makes a lot of sense, but I think that doesn't translate so well even to the UK. Someone suggested to me Überwinden. Now, I don't speak German, and that sounded really cool to me. And I have since learned from showing this to other people that he didn't speak German either, because it means something completely not appropriate or not in context in German. But it looks so cool, so I'm really sad about Überwinden, because it's almost perfect, except for the small matter of actually meaning the right thing. But with all of them, the point is that climate solutions, they can make everything better. So, when you think about the zombie servers, for example, there would be no downside to turning those things off. And there would be a $26.6 billion upside, which would be a lot of money that we could spend on ice cream and licorice or waffles or something. And in general, turning things off saves a lot of money. But it's, that's sort of simple and easy. Okay, yeah, if you turn things off, you save money. But there's some other benefits that are maybe less obvious. So for example, renewable energy is 9 times cheaper than things like coal energy. So why wouldn't you want to run on renewable energy if you could? And you can see this if you look at some of the hosting numbers. So for example, if you choose to host in Montreal, it's using 88% less carbon than hosting the same workload in London, and it's 15% cheaper. So except for data residency and latency, maybe, there is no reason not to host in Montreal. But then maybe if you're worried about that, Stockholm has similar savings in cost and carbon. So again, usually there is something, unless you're trying to host in Asia, usually there is a small shift that can get you onto a greener workload and save money. And I think when you think about the Vroom model, which you probably don't remember because I made up the name, but what that was showing was that when we went to a workload, or when we went to a framework that had better throughput, which is so much nicer to use, and faster and gives us better response times so our customers are happier and everything like that, we're also saving carbon. And I think that's so counterintuitive, because if you think about something like a car, like I had to buy a car recently, and I really wanted a car with a huge engine that was going to go really fast. And I couldn't buy an electric car for reasons. And so in the end, I had to sort of go for one with a small little engine that went put, 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 because I wanted to be environmentally responsible. But when you think about choosing a framework, you want the one with the big engine that goes fast, because it's actually also going to be more environmentally responsible. And there's so many examples of this in IT and then just more generally. So I love this quote that climate solutions are just better ways to do the things that we want to do. And this idea that we have to sacrifice everything to save the planet is wrong, because a lot of these things are actually better than what they're replacing, as well as being more environmentally responsible. And we definitely see this with Quarkus, that when people switch to Quarkus, they're so delighted with the developer experience, as well as saving all the money and saving the world. So really, this isn't sacrifice, this is advancement. So, for the too long didn't pay attention takeaways, trick 1, the Vroom model says faster is greener, hooray. Trick 2 is that the economic model says cheaper is greener, hooray. Trick 3, which I have put in the wrong order for reasons, is that something like Quarkus, if you choose that fast and energy efficient framework, that's going to be greener. Architect it to be able to turn stuff off, which you can call light switch ops, and then I'll get really happy. And then the final trick is choose your hosting wisely. And with that, hopefully, this is something that we all can do, and we all make a difference. And the more of us do it, the more difference we make. And with that, thank you very much. And finally, don't forget to vote in the JSpring app, partly because it's running on Quarkus, and that's cool, but also because the feedback really helps the program committee, and it really helps the speakers as well. Thank you very much.